Hopefully the sound plays.
Imagine a world where you can lie down in a machine and be told not just what's wrong, but also how to fix it, and in a way that suits you best. Imagine healthcare that uses every piece of you, from your DNA to images of your body, to help keep you healthy and prescribe personalized treatment just for you. Imagine what doctors could do if they had artificial intelligence on their side, diagnosing disease faster and more accurately than ever before, leaving them free to help their patients through the treatment process. Wait, so I know what you're thinking. Artificial intelligence, or AI, is sold as this magical thing that can solve all of our problems and make medicine awesome for everyone. But how much of this is actually achievable now? And how much is just hype and misunderstanding the capabilities of the algorithms we have available? Well, let's take a look. So we might be a little while off the Star Trek style tricorder, but AI, or more specifically, artificial narrow intelligence, is making headway into medical fields like radiology, dermatology, and ophthalmology to assist doctors in reducing the diagnosis time and improving accuracy. Currently, with the volume of data generated and the increasing demand for diagnostic imaging, the average radiologist is interpreting an image every 3 to 4 seconds for 8 hours a day. Now imagine if radiologists had AI acting as a second pair of eyes to help them. In the case of skin cancer, the same algorithms that can tell a cat from a dog on Facebook have also been trained to detect suspicious moles from images to the same accuracy as a board-certified dermatologist. This style of model has also been used to identify those with diabetic retinopathy, a condition that causes blindness due to damage to the retina. The impact of this is enormous, given that the number of ophthalmologists available to diagnose this condition is so low compared to the number of people with diabetes that many people go undiagnosed and end up with preventable blindness. And what about the holy grail of healthcare, personalised medicine? Although we're not quite able to predict disease onset or choose perfect individualised treatments with perfect accuracy, more and more research is being done into the predictive power of your health data and the insights it can deliver. Given that the Electronic Health Record Systems, or EHR, in the US alone will soon be documenting over 1 billion patient visits per year, efforts to distill this mammoth amount of data into useful predictions about likely treatment outcomes and diagnosis events are already underway and achieving significant accuracy. Using an algorithm inspired by the language models used to predict the word that comes next in a sentence, researchers were also able to do the same with treatment and diagnosis codes. And it's not just EHR data being included. Medical imaging is starting to play a role too, like researchers who showed that retinal fundus scans, images of the back of the eye, had useful features for predicting an individual's risk of cardiovascular disease, something that was previously thought to be absent or unquantifiable in such images. Again, our cats and dogs algorithm was retaught to look at retinal scans, and this time predict important factors like diabetic status and cholesterol levels. And in the spirit of bucking the trend of AI being a so-called black box, meaning that no one really knows how they work, using new saliency methods, the team can show just what the algorithm was essentially looking at when it made predictions. So in short, while AI might not currently be able to do all of the magical high-tech things that we see in movies, its impact to humanity should not be underestimated. Even with current algorithms, people in places where there are few specialists can benefit enormously, and in medical areas that are traditionally difficult, doctors can be given a helping hand. Like with some diagnostic methods, such as interpreting mammograms, where up to 1 in 2 women are falsely told they have cancer, or chest CTs, where 30% of images with pathological features are misdiagnosed. So while not every healthcare dream is currently a reality, with the research out there now, a Star Trek future might not be too far away.
So that's a little bit of what we do, a little bit of the stuff that's possible, and a little bit of, hopefully, after today, things that you'll be interested in doing and things that you will feel empowered to go forward and learn how to do. So this talk will break down into the first part, some stuff about deep learning, how can you get into deep learning, what are the different sort of levels of expertise, do you need a PhD, all that kind of thing, and then we'll give you guys a little bit of a break, and then we'll go through the Jupyter Notebook tutorial on the what we call the Helloworld of Machine Learning. So I will take a seat for this because it's been a long day, but we'll go through what we've got. So a little bit about me. I started as a linguist, so this is me in China. I made the jump to engineering because I wanted to learn how to code, I wanted to build robots, and I wanted to help people with, combining tech and healthcare solutions. When I graduated, I joined the oil field to make a bit of cash. Had my own software consulting business before I found Maxwell Plus, and that's what I'm doing now. So originally we started as Maxwell MRI. We've recently rebranded because instead of just looking at MRI images for prostate cancer, we're now looking at lung cancer, breast cancer, and some neurodegenerative stuff as well, and not just MRI, looking at CT, other medical imaging, as well as blood markers, genetics, combining it all to learn more about people's health. And here I am at WIML, Women in Machine Learning. It's my favourite thing. So, what's with all the acronyms? We'll start with that. So basically you've got your artificial intelligence, which is kind of the umbrella category and what people use when they're not sure if the audience will know what machine learning is or what deep learning is. Typically though nowadays, a lot of the focus is on narrow applications, so specific algorithms that are good with health data, with finance data, with text, that kind of thing. And I guess it sort of leans towards the more Gucci deep learning neural network type stuff. So machine learning itself, you'll notice I rebranded the tutorial to deep learning because machine learning actually covers a lot of the sort of older, more traditional methods of analysis, particularly so there's support vector machines, decision trees, PCA. I'm not going to go into super depth with those. You can definitely look them up afterwards, but they're more focused on handcrafted features. So it was when people knew that, for example, if you're analysing house prices, you might use the number of rooms, you might use the, size of the house, you might use what neighbourhood it's in, and those are all features that you yourself have extracted from the data. Whereas the deep learning comes in where you may not know what features you're looking for. So in the case of images, how can you tell an algorithm, what is a cat or what is the letter, the number 3, for example. There's no explicit features that you can pull out that are, super generalizable across a very large set of data, and that's where deep learning comes into play. So, how do you even get into all this stuff? How can you do deep learning without all of the learning? So at Maxwell, we have 3 different levels. So the first one is the level 1. So hopefully we'll get you guys kind of to that level today and on your journey to becoming, the next deep learning kind of experts. So to start with, level 1, you kind of have done some vanilla models with, there's a few standard data sets. You may know what to do, but not why it works, and if it's broken, there's a tendency to not know how to fix it. And a lot of people refer to themselves as machine learning enthusiasts or deep learning enthusiasts. And this is a good place to be. As the dog says, sucking at something is the first step to being sort of good at something. We all start here, and the key is to just not give up. It seems a little bit confusing. There may be some mathematics that you might not have touched on, but there's a lot of resources out there, and the point is to just keep reading, keep learning, keep asking, and keep experimenting. and the level 2s. So these ones know enough to be dangerous. So often they know best practice and they can use it to make their models better, but often the underlying theory may not be there. So I'll just ask, who here would classify themselves as a software developer, but not necessarily an engineer, so hasn't really done an engineering degree? Anyone? No one? No one's a software developer.
I am a software developer, but
Yeah.
I've got a Bachelor of Engineering as well.
Yeah, cool. So I get my question with that is, has anyone done linear algebra recently? Yeah, cool.
Recently.
So, recently. So yeah, a lot of the machine learning and deep learning stuff has like quite deep mathematical and statistical underpinnings, and a lot of people will think, oh, well, can I do it if I haven't done those before? And the level 1s and level 2s are kind of those people, so they know how to implement different things. They've used various model architectures on different kinds of data. They may understand sort of best practice and like principles for fixing models where they don't predict the right thing, or if you run your code end to end and it breaks and you're figuring out why. But often it's the mathematical and statistical parts that they may not completely understand. But as you'll see, these people can still apply their skills quite well and achieve some really good results with what they're doing. Yes, and the keys to success: fine-tune what you don't know and start going back to first principles. This one. So these ones are the level 3s. At this stage, we're kind of thinking that you either have to do a lot of mathematics courses and statistics courses, and a lot of it is just exposure as well. So the more you build, the more you experiment, the more you look at what other people have implemented, research papers, if you read through those, look up what you don't know, that's where you sort of get to this level. But again, working in industry, you often don't need to be at this level. You can start as a 1 or 2 and then build your skills to get to this level. So what can you do to get started? For the level 1s, tutorials like this. There's also a whole bunch of good courses like Fast AI, Coursera's Machine Learning from Stanford. That's what I started with. It'll give you a very robust foundation of how to implement the basics of machine learning and getting into deep learning for your convolutional neural nets and recurrent neural nets. Also, there's existing data sets, so simple things like MNIST, which are your digits, CFAR, which are like the little pictures of cats and dogs and birds and trains. There's a lot of things out there that you can experiment with that are well documented. There's a lot of tutorials to learn from there. Get familiar with the lingo. There's a lot of acronyms and weird terms being thrown around, but again, there's a lot out there to help you understand what those mean. And Kaggle. Kaggle is, has anyone heard of Kaggle? So a few people. So it was an Australian website for data science and machine learning and AI people to compete to win prizes for the algorithms that they implemented, and recently got acquired by Google, so good work. But there's a lot of like existing tutorials, kernels they call it, so the IPython notebooks on how to do different things, how to do data processing, explanations of all sorts of stuff. Cool. And then level 2, get reading. So one of the things that we do is we implement papers. So there's a lot of things, a lot of cutting edge research coming out effectively every week. And the best way to learn and stay up to date is to read through those, try and implement some of it yourself, have a look at other people's implementation, and then work on, figuring out why it works and then how you might extend it to whatever application you have. So the basics of the AI kind of process, the first thing to ask yourself is this even an AI problem? Because a lot of people will say, oh, if we just throw AI at it, then magically we'll have this outcome and it'll do exactly what we want. And so it doesn't always work like that. So often you have to look at whether or not what you're trying to do is feasible, and most importantly, whether or not you have the data to do it. So the reason machine learning was so successful, so machine learning compared to deep learning was so successful, is that it works on smaller data sets, because you can extract the features that you know are important and learn those to predict quite well. Whereas deep learning does require a lot of data because it needs to pick out the specific features across a huge set. So those are some considerations there. Then you've got your inputs and outputs. So selecting what kind of data you want in, how you might need to process it. The next step is selecting the model architecture. So often you can look at what people have already done, I guess what your goal is, and typical models that you might use to achieve the goals that you are looking to do. And then you run through your training and testing. So a lot of that considerations are time. So the papers that are coming out are, we use 15,000 TPUs with Google, so you may not have those sorts of resources available. And then in the wild, so that's the favorite one. Often the data that you train with is not the data that you get. So I think Andrew Ng has a very good book called Machine Learning Yearning, which talks a lot about that, how people train models on, recognizing cats in pictures, and then when they get pictures of cats from their users, they're all the, blurry selfies with my cat, that kind of thing, and it can't pick up the cats at all, and people wonder, like, oh, what happened? So those are some, that's a good resource to look at if you guys are into that. Cool. So these are my details. I'll give you guys a 5-minute break to jump on that Git repo there, grab the tutorial if you'd like to have it on your computer, and then we'll go through it.